Okay. Interrupt live. Okay, so as I said, today is the last class and everybody's happy. Okay, it's about the hierarchical scheduling. Let me first then introduce the problem from my perspective. What's the motivation for this? So when we have many applications, here denoted by app A, app B, app C, possibly composed by each of them composed by some tasks, I mean 3 tasks, 2 or 3 or whatever. What's the problem when they are all running on the same machine? And well, here we have a machine and a scheduler, which is scheduling tasks coming from all the applications. What is the problem with this with this approach? With the approach depicted in this figure? The problem is that if any misbehavior happens in application A, such as, let's say, a task which takes longer than expected, or it goes in a dead live lock if you want, basically it may cause a misbehavior also in other applications, okay? Because if a task here, let's say task tau A1 has the highest priority among all tasks, it takes forever because it is in a live lock, well, basically, I mean, the misbehavior in this application affects also these other applications because those applications will never run, right? And also, when you are at the point of, let's say that this scheduler is fixed priority, if you want. When you are to assign priorities here, basically you have to compare the priorities of tasks belonging to different applications, which is something that may be not so easy to do. How do you compare if task 1 of application A is more important or needs a higher priority than task 1 of application B? These two applications may be, I mean, different and then hard to compare.
But does it matter? Isn't it enough that all these tasks meet their deadlines?
What?
Does it matter? I mean, does it matter? We just need to find a priority order in such that all the tasks meet their deadlines. Right?
Yes.
So, but it doesn't really matter which task executes first. I mean, if it is.
Yes, as long. Yeah, but the point is that you may also. I was also going to this point. You may also violate in here. You need to have the knowledge of all tasks into the application. So you need to have internal knowledge of the application. And this may also violate, if you want, like intellectual property boundaries. Let's say I deliver you an application, a standalone application, and I don't want to disclose to the scheduler any information about how my application is composed. So there is also something about intellectual properties. And then when a new application joins, let's say you have another application coming in, you have to assign the priorities of its tasks and in comparison to the priorities of all the tasks that you have already. So where do you put these tasks? Between tau A3 and tau C2. So I mean, you have to compare things which may be not so easy to compare. So what is a solution that is quite common in the literature is to to introduce the concept of virtual machine, and then basically you have the physical machine which is scheduled to virtual machines by a global scheduler. So we have a global scheduler here which is in charge of scheduling the actual physical machine to virtual machines. Okay, and then we have a local scheduler, which is depends on application. So we have local scheduler A, local scheduler B, local scheduler C, which schedule the tasks corresponding to the corresponding application to the corresponding virtual machine. Okay, so in this way, basically, we isolate application A to run onto virtual machine A using its own scheduler A. And then the same with B and C, okay?
Which kind of scheduler is the scheduler?
Which you mean EDF? It can be, typically, I mean, in reality, what is, if you want, it's typically a static time partition. Typically, what it happened, let's say, in automotive, which may be something that you have more experience with. Here, you just divide time in a.
And why it does not have any sense?
No, it has many sense even in other cases. I mean, you could see it as the hypervisor, which is scheduling virtual machines, and here you could use Yuri's schedule, right? To schedule virtual machines, and here you could have Linux. So you could have an hypervisor here, which has all the processors available. And so here you have the hypervisor scheduler, which could be, which could be scheduler if you want. And here,
for example, if the local scheduler are, for example, remote only. The global scheduler is also remote only.
Okay.
So does it have sense?
It does, but it's not a necessary requirement. Here you could have anything, and here you could have anything else. Here the roles. I mean, here, for this guy, on the bottom, it has the physical machine.
But if the global scheduler is not some guy that reserves a bandwidth.
Okay, let's say that here that you have rate monotonics everywhere.
Yeah, I can have, if there is rate monotonic everywhere, I can have only one global scheduler for all the.
No, there is a difference, because when you have rate monotonic, let's say fixed priority here, here, and here, basically, you have just, when you have fixed priority here, you just have to set the ordering of priority of these tasks. Here you have to set the ordering of priority of these tasks, among these tasks only. And here, you have to set the ordering among only these tasks. You do not have to set the ordering among all these tasks and these other.
If I assign a priority in the global scheduler according to fixed priority,
okay,
then I have a global order.
Yes, easy, of course. Yeah, okay. If you have, well, but it depends also on the implementation. If you have a fixed priority here that says anytime a task here is ready, then schedule it. Then, of course, if you want, you can see it as every task here has higher priority than every task here, which has higher priority than every task here. I mean, of course.
But in that case, so if suppose the global scheduler is rate monotonic and the local are also rate monotonic.
Mm-hmm. Yeah, but rate, I mean, I don't understand. I mean, rate of what? I mean, when you say rate monotonic here, is rate monotonic respect of what? What's the rate?
That's it.
Okay? So when you have fixed priority, then you can set priorities among virtual machine, but you know, there is no. Okay, so. Yes, sorry, I forgot about your question.
When we say schedulers, it means that the scheduling policy depends on the parameter of the task set. Okay?
Yes.
Maybe deadline, priority.
Yes.
But for the global scheduler, what kind of, like, from the VM point of view, like VMA, VMB, VMC, like, what are the parameters? Like,
yes, like
A has a
okay.
deadline.
Yeah, I will come later to this point. I mean, to give you just a quick answer right now. I mean, the simpler way to go is that virtual machines appear to the global scheduler as tasks.
As one task.
As one task.
So when you say one task, it means one task has some kind of deadline also?
Yes. You have a deadline of the so-called server implementing the virtual machine.
So it means that if a task in virtual machine 1 is active, it may not get the process immediately.
Right.
It could go to the second.
Exactly, because you know to get for this task to get the machine, it needs to be scheduled over here, and this virtual machine needs to be scheduled over here.
So it means that for the global scheduler, the VMA is like a one task.
If you want, yes, if you want, you can view it this way. Yeah, I mean, but that depends on the global scheduler policy. If the global scheduler policy is implemented, as we were assuming with Fabio, as a static partition of time, then it's just a piece of time, right? So you may decide that, you know, this virtual machine is always allocated between. So you set the global schedule maybe like a periodic scheme, let's say with period 4, where you assign. From 0 to 2 to this, from 2 to 3 to this.
Round robin.
round robin with different budgets. Yes, testing could be round robin.
Kind of.
Yes, right. Okay, so what's the advantage? The advantage is that, right, in this case, misbehavior is confined within an application and the virtual machine. So if you have a task running longer than its time, then of course it does affect the application because you have done your application design not properly. So it's not a surprise that if it affects the application itself.
That depends on the operating system implementation. I mean, like you could have an operating system which enforces budgets, time budgets.
Yes, right.
Allowing the task to execute fully.
Yes, of course. I mean, it depends also on the global schedule. If the global schedule allows a misbehaving virtual machine to run forever, if the virtual machine is asking time, then of course, in this case, this misbehavior is propagated everywhere. But if the mechanism here confines the time to in a precise way, then of course, if a misbehavior here,
but
it is stopped to be propagated.
But can't we not enforce it directly? Like you schedule all the tasks and enforce budgets for all the tasks.
Yes, you can. From the this way you separate a bit the effort, right? Because here you just do the separation of concerns, if you want, from the budgets at application level. So if you have a so clear, distinction, I mean, otherwise you would need to specify at the global scheduler level the budget that you have at each task, at each application, which may, be something you may don't want to do, right?
It means application layer characteristics, like application A has a higher priority or application B has a higher priority.
Yeah, I mean, application A and B may be anything that is currently running on the same physical machine. I mean, on yourself, or you may have, the application which is in charge to reconnect with the network on the one that you are a browser. It could be anything, and may be independent of one another, right? Okay, and as the final, as I said, the task priority semantics is confined within the application. Okay, so what model do we use? Well, as application, we use the same sporadic task set model with computation time period data. It could make it more complicated, but in the course I have no time to do more complicated stuff. And local scheduler, it could be fixed priority EDF, like at the local scheduler level. And we restrict to a single processor machine. Extension to multiprocessor is possible. So, I mean, there are papers, but just have no time in the class to go into this detail. But, conceptually, it's not that different. Okay? And then the question is, what model do we use for virtual machines? So, what model we use for the time provided by virtual machine? Okay, what's resource model? So, the virtual machine, the model for a virtual machine, now, well, so far, the task set could consume the entire resource available because the processor was entirely available to the application. Now, the processor is not entirely available to the processor. It's partially available. So this model of virtual machine must capture this partial availability. Okay? And so I have two definitions, which are, one is like in words, informal, and the second one is a bit more formal. So we model the virtual machine. Basically, we model the amount of resource that is provided from a virtual machine to an application by the so-called supply-bound function. So we define, let's see first the informal version of the definition. So we define supply-bound function as BF k of t of the k virtual machine, so k is the index of virtual machine, as the minimum amount of resource that is available in any interval of length t, okay, so t is the length, among any possible resource schedule. Resource schedule is the schedule of the resource that the global scheduler gives to the virtual machine. As we said before, we have the machine here, the global scheduler, and the global scheduler assign resource type to the virtual machine. Okay. More formally, let us denote by G the global scheduler if you want. And then let's denote by legal of G the set of all possible schedules of resource to virtual machines. So basically, right, that's just the set of all schedules of the global scheduler, what the global scheduler can allocate to virtual machines. Then the supply bound function of the virtual machine KLT is defined as these two infimum, one after the other. Let's see. Infimum over what? Over all possible schedules within the legal ones. Okay. Then once we have this schedule S, we do the infimum on T0, and T0 is going to be the boundary, the left boundary of the interval of integration. So here on T0, so then I do the integration between T0 and T0 plus T. So here you see the T here is the length of the interval over which I'm integrating. So I'm integrating between T0 and T0 plus T, so I have this interval T, and I'm integrating what? I'm integrating the indicator function. So one is the indicator function of a set, which basically means the function, it's 1 when we are in the set, it is 0 when we are not in the set. Indicator function, what set? Of the schedule of the K virtual machine. Okay, let me make an example. What?
-1.
S to the -1 is the inverse, because I defined in the first class, maybe you missed the first class. S, I defined the schedule S. S, I define, I mean, now we have only one resource as a function that goes from the time set. Let's see, well, in this case, it's the half line, so let's make it easy. From 0 to infinity to, well, in this case, let's say the set of virtual machine. I denote it with letters. I, B, C, D, whatever. So this is the set of virtual machine. Okay? So basically, S it schedules time to virtual machines. It says now it's you, now it's you, now it's you, it's you. Okay? This is just the schedule. So the inverse, basically the inverse is so basically S minus 1 K is a subset of the half line, okay, on which the time is allocated to the virtual machine K. Okay, just to make an example, let's say that over this is the timeline. Let's say that I allocate from here to A, from here to B, from here to A, and from here to C, if you want. Then S minus 1 of K, the inverse image of A, is this set plus this set. So S minus 1 of A is this to get union with this. Then S minus 1 of B is this, and S minus 1 of C is this. Okay? Okay. So basically, let's now put this definition in practice if you want. What does it mean? Well, I have examples later on, so I don't need to do it now. Okay. Let's compute it for some example. Let's assume that the global schedule provides resource to the virtual machine A according to this schedule. This schedule is just the union over all intervals of this form. This is the static partition that, for example, we were mentioning before with Pablo. So these intervals then are as follows. are allocating resource between 0 and 1, then 4 and 5, 8 and 9, and so forth. Okay? That's how we are doing. What is a supply bound function of A? Okay, we have to make the infimum over the set of legal schedules and the set and T0. Here the set of legal partition is only 1 because this is a static partition. So the only way to partition, the only way to schedule the machine to virtual machine is this one. So I mean, legal is just a single term. So if you want, we can say that legal of G is equal just to S, to this schedule of this. Okay, now we have to compute the inf. We have to compute inf on T0 of the integral between T0 and T0 plus T of a function that is like this. Okay, which goes 1 here and 0 here. Okay? So of this 1 of, to maybe its form of S, it's a function of well, let's call it of S, yes. Okay, so what is this equal to? Okay, well, how do we do this info? First of all, it's quite, I think we can formally prove it without making not too big things. Let's say that we can restrict the search to all T0s, which are the end of some interval where it is allocated resource. Why this? Let's say that I have, for any T0 here, so I write this and then I kind of prove it, okay? T0 belonging to, if you want, start of idle. Start of idle, some idle. Of the same stuff, of the same. So I'm saying that it's necessarily sufficient to restrict the search among the T0, which are the start of some idle interval. Why this? Let's say that I have a T0 here. Okay, if I move back to the let's see, not the latest. Yes, the latest. No, I mean to the point, to the start, to the idle that you have on the left. You can only put less resource into the interval because by shifting leftwards in this interval you add nothing because it's idle. In that interval, maybe you lose, maybe you do not change anything. So. Well, you can only do worse. So the infimum here certainly occur at some, you don't lose anything if you do the infimum when T0 is the start of some idle. So we can restrict here with T0 here, T0 here, T0 here. Okay? And because of this periodicity, basically, I mean, considering T0 here or here is just the same because the scheme repeats forever. So here we can do the same with T0 equal to 1 if you want. Okay? So if you do with T0 equal to 1, basically now we can, talk. So we have to do the integral between 1 and T plus 1 of a function of this function. Okay, and what is the integral from 1 to T plus 1 of this function? Of this 1 of S minus 1, okay? is, I'm not writing, I'm just drawing, it's something that is 0 until 3, because from here to here it's 0. Then it grows with the slope 1 until 4. Then it is flat until 7, goes up to 8, and so on and so forth. Okay? Is it clear? Clear to everybody? What? It's top. It's flat until no, it's flat until 7, because we are starting to integrate it to 1. Okay? Because this is the length of the input. Okay? Okay. Let's make another example. Now we have a static partition, which is a bit trickier.
So, Enrico.
Yes.
So, given a set of applications.
Given a set of applications.
Is it possible to derive the supply bound function such that all tasks meet the deadline?
Is it possible to say yes?
How
yeah, it's something probably of its life. So given an application, the set of supply, yes, you can, well, what you can do, you can derive constraints on the supply by function that guarantees you schedulability of the application. And then whatever supply by function that satisfies the constraints, yeah, but it's something that we will see. It's this class. Okay, so let's see what happens to this. Here we are considering, again, a static partition of time, which has a period of 12 in this case, because you see here, basically, we are making the union over k, all the integers. So we have 12k, 12k, so everything is periodic by 12. But then the resource is allocated only at this interval. So I'm drawing maybe here. So from 0, there is no resource until 2. So okay, period of 12. Let's draw 12 here. So here we have 6. Here we have 3. Here we have 2. Okay. So here was 6, 9. Okay. So we have resource from 2 to 3. And then resource from 5 to 7. And resource from 10 to 12. So it's 6, 7, 8, 9, 10, 10. And then it repeats. So it repeats, it means that, so from 14, you have 1, then you have holes of 2, right. Up to, yeah, maybe 19, maybe. Okay, something like that. Okay, it repeats. So basically, well, let me draw the period a bit, and so on and so forth. Okay. Okay, now let's try to compute the supply bound function in this case. So as I said before, we can restrict to the set of start of idle intervals. Okay, here the idle, since the pattern in a period there are 3 idle intervals, the possible start time of idle interval are 3. So it's this, and this. Okay. So if we start here, if we integrate, basically we get a flat. I want to try to do it properly. 3, 4, 3, 7, 8, 9, 10, 11, 12, then it repeats. So it is 12. Okay, so if we start integrating here, we stay flat until 2. Then we increase by 1, flat until 2. We increase by 2, flat for 3 units of time, and then increase by 2. Okay, and we reach 5 because 5 is the overall. If we integrate starting from here, we are flat until 2, and then we increase by 2. So basically, we go here. Well, I want to try to do it differently to remember the points where we started with. So here I do it dotted. Dotted is when we start T0 equal to 3. And this is T0 equal to 0. Okay? So then we go here, and we are flat for T time units. Okay, then we increase by 2. By 2. Okay, then we are flat for 2, and then we increase. Okay, so what we can notice already now is that since at some point we have to do the infimum of this function, the infimum may be taken starting, okay, well, the line is solid, the infimum is taken when T0 is equal to 0, but here the infimum is taken when T0 is equal to 3. So for the same T, the T0 which produce the infimum may be different. So here, for T here, the infimum is taken for T0 equal to 0. Here, the infimum is taken for T0 equal to 3. So it may be different. But we miss also the last case. The last case, actually, we have another possible case. So if we start here at T0 equal to 7, here I do it, well, I don't know, kind of, yeah, wavy line. Wavy line, we have a wavy line here. Wavy line. So here we do like wavy line here. So the wavy line is T0 equal to 7. Now we are going, the wavy line goes, no, now we increased already, right? Okay, here, so now it's flat by 2. Okay, then it increased by 1. Then it's flat for 2 units of time. Well, I don't know, maybe I'm doing wrong, no. Maybe it's okay. It was supposed to be here. So maybe it's here. Yes, and then it increases. Oh, okay, something like this. Okay, and you can see that here actually we have another point. So here, so in the end we have to do the infimum. So let's conclude. So the supply bound function is this, right? Which then it repeats, okay? Which then repeats forever. And as you can notice, for different values of time, the infimum may be given starting from different T0. Okay? Is there any question here on this? No. Now let's make another case. In both cases we have seen so far, the schedule, the global scheduler, had a fixed schedule. The global scheduler had a fixed schedule, which was repeating over time, which was a static time partition, which is something that happens, okay? That is actually very common practice, if you want. Now we consider a different case. It's the case where the virtual machine is implemented by the so-called periodic resource servers. Basically, it provides, so basically, let's say, the virtual machine, which I draw like here, so it was VMA, is a periodic server, which is characterized by budget P and a Q and a budget P. And then the budget, well, let's say QA and PA, if you will. And then the same with other servers. And these servers are scheduled by the global scheduler. Okay? Now, which guarantees a budget QA periodically, every period PA. Now, legal of G, so the set of legal schedule is, is not anymore fixed, but it can depend on many, also on the others. So the point is that when we do the inf of the schedule, when we do the inf, you remember in the expression there was inf of S into legal of G. Okay? Now, we call, if it exists, because it may not exist, if it exists, S prime such that S equal to S prime, now let me wait a second before writing. Okay, SBF of T was written as the inf for all the schedule among the legal ones of a lot of stuff which was function also of S. So we have to do the inf indicator function. So S appeared in the indicator function. So if exists S prime such that the inf is given by S prime of the same stuff, then S prime is called the worst case resource schedule. Okay? This is very typical in real-time system, right? So you want to do the infimum, the worst possible. You want to check what is the worst possible schedule of resource that gives you the minimum amount of resource. If you can find a schedule S prime which for all T provides you the worst case the resource schedule, then you define S prime as this, and then you can just analyze the rest with the schedule S prime. Okay? And actually for the periodic server, the schedule S prime exists and is built in this way. So we know that the global scheduler will allocate always resource, Q resource in this interval, Q resource in this interval, Q resource in this interval. So what is the worst to put the resource into this interval? Well, we could prove, but I will not prove, that the worst way to put the resource in this interval is this one. And when you have T0 starting from here. Okay? So the worst way to put the resource into the interval is that T0 is the interval where you start to accumulate useful resource, right? So the worst possible condition is when in this interval the resource Q was just allocated before, and then you start the T0 here. This way you have the longest possible idle in this interval, and then the next resource is given at the end of the interval. So you have an even longer idle interval here. So In this way, you have a possible, potentially, you have this interval with no resource supply equal to 2 times P minus Q, right? So this is okay. And then after 2 times P minus Q, you start to have some resource, and then you have an interval with no resource, take Q resource, and so on. In fact, the supply function in this case is exactly this one. 0 until 2 times P minus Q, then it increased by Q until 2 times P minus Q plus Q, so this is Q. Then it is flat for P minus Q, so this is just P minus Q. Then it increased by Q. Okay, so basically the degree of freedom introduced by this, so by this minimization over any possible legal schedule, basically increase increase the length of this interval equal to 0. Otherwise, in the other case, let's say that you have a static schedule of resource where you always provide periodically Q resource every P statically at the beginning of the interval, for example, then in this case, this interval would be just P minus Q, okay? Instead, with a degree of freedom of allowing the resource schedule to be anywhere in the interval between 0 and P, then of course you add an extra degree of freedom onto the infimum, and of course this is going to be smaller than this function. Okay? And in formula, you write it. Okay. And in formula, you write it in this way. Yeah. Okay, so this is just the formula of that expression that I just drew on the whiteboard. Okay, this also explains a bit why this is called sometimes hierarchical scheduling, because basically it is about to schedule a set of tasks within another task. And then below, you can have a set of virtual machines that you can all see as tasks, and you can combine them into another task, and so on and so forth. If you want, you can see it as a hierarchical schedule.
But does it make sense to have more than one level of hierarchy? I mean, in an actual case.
I have no experience with actual cases. No, I don't know. I would say no, but maybe when you are into this integration phase, well, where you buy a component from third party and then you combine, and you build an application, and then this application has to be combined with other applications which have been built by other people.
Okay.
So I don't know. Yeah, maybe. And then everything goes into another bigger, I don't know. Maybe yes, maybe no. Okay, so how do we perform schedulability conditions onto this type of supply function? Well, the conditions are very simple. The usual ones, with the only little difference, let's say fixed priority, for example. For all tasks exist a point such that the computation time of the task and the interference onto the task is less than or equal than the supply by bound function. No surprise. Okay, so here in the fixed priority condition, where you have the processor available, you have t, because t is the amount of time that you have available up to t. Now, since the amount of time available up to t is not t, but it is SBF of t, then with no big deal, we just write here on the right-hand side SBF of t. With the same with the same argument, here we write that for EDF, the task set is EDF schedule over a virtual machine with supply bound function SPF, if and only if for all t the demand bound function is less or equal than SPF. Okay, so this is just a straightforward translation of the concept of supply bound function. Okay. Right, so testing, let's take the case with the periodic resource server is very common, and so this expression appears very often actually. But what's the point? The point is that sometimes making the test with a supply bound function, like in this form, may be too complicated. And the people may also, here I remind you, we have 2p minus q, and here we have steps of q, and then here then we start to put periodics, and this is q, if you want, and so on. So sometimes we want to find a lower bound, because the lower bound is safe. If this condition is true for a lower bound of the SPF, it's also true for the real SPF. So that's why the lower bound is safe. So a linear lower bound is something that goes through here. Okay? So for a given SBF, you may want to find a linear lower bound defined as the max between 0, because we have 0, and the linear bound. The linear bound that has slope alpha, and that intercepts the x-axis at delta. So we want to find this as tight as possible. So typically we define then alpha as the limit of the SBF over t, so that somehow the slope on the long run, so the amount of bandwidth, if you want, this is the bandwidth, right? How much time you provide over some length of interval with the limit, okay? And then we want delta to be such that this line is below, and then you define delta as this way. Right? So, okay. Typically, we take alpha equal to, I don't know what I meant with this. Typically, we take alpha equal to dots. I don't know. Okay. Okay, alpha then is called the bandwidth of the virtual machine, and delta is often called the delay. The delay. Okay. Yes, this is also important. So, by this definition, delta is quite obviously always greater or equal than the longest interval where the supply bound function is 0. Okay? This is, I mean, it's not always equal. I will show an example where delta may be even larger than this value. But of course, it cannot be smaller, right? Because if it's smaller, then it's not a lower bound. Okay? Let's see what is the linear lower bound to the server which provides a budget Q over a period P. Well, with no surprise, if you draw that expression, well, basically, since here you have a period P and the height of the step is Q, if you make the limit here, you get Q over P. I guess you believe it. Okay. And if you put this line with slope alpha equal to Q over P at the leftmost place, basically this line goes here and touch here. So basically you have delta equal to 2P minus Q. Okay? You cannot move this more on the left, otherwise it's no longer a lower bound. Yes, I have also this example. This is an example that I typically like because it shows an interesting feature. Let's say that we have let's compute first the supply. Let's compute the supply bound function of this scheme. This is a scheme with a period of 6, which provides time, which has an idle here, provides time between 1 and 2, and provides time between 3 and 6. Okay. So if you compute the supply bound function, supply bound function is like this. It's flat here. It has a step here. Flat here. There's a step of 6. And then it's a piece. Okay. So now, what is alpha? What is the bandwidth of this scheme? You need some water. So what was the bandwidth? The bandwidth is the amount of resource you have in the long run. If you have a scheme that periodically allocates, so here from 0 to 6 you have that, but then it repeats. Huh? 4 over 6. Which is good.
But that's like the utilization, right?
Which is?
Like the utilization.
Like the utilization. Now, can you also see what is delta? You have to think. So you have to think of a line with a slope 2 over 3. So 2 over 3 is like this one, right? Because here you have 4 and 6. But however, this is above. So this line, you have to bring it below. Well.
No, but that is the line over top. Why? What was that?
No, this has a slope of 2. It's not a lower bound.
Ah, okay.
Yeah, okay. I was just drawing a line which has a slope of 2 over 3. Okay? And then you have to put this line in a way that is always below. And you can, if you do the math, you will find out that this line has to go through this point and will not touch this point. And I think we get delta equal to 1.5. Yes, so we have 1.5. 1.5, which is largest, three largest, and the longest idle time. The longest idle time was 1, while delta is 1.5. So a concept, I mean, a quite common mistake I actually find in papers sometimes is that, I mean, the people tend to say that in this case the delta is 1, if you want. But delta is not, you cannot lower bound the supply bound function with delta equal to 1, otherwise it's not a lower bound.
Alpha is bandwidth.
What?
Alpha?
What?
Alpha.
Alpha is 2/3.
5 by 12.
Cazzo è schifo. Ah no, io ho reported a different example. Completely crazy. Cazzo fa? No, yeah, it's 2 over 3. Yeah, no, it's completely gone. No, yes, I mean, I think it corresponds to another example. Yeah.
But so what is the physical interpretation of delta?
Delta, the physical interpretation of delta is not as straightforward as the bandwidth alpha, but it is somehow, if you want, a sort of delay with which you receive the bandwidth alpha.
That's the first delay.
Let's say, let's compare two servers with the same bandwidth alpha, let's say 1/2, and delay 0 and delay B, and big delay. The point is, well, later we will see when we get to the schedule tasks. The point is that the one with delay 0 can give is more prompt in giving you that bandwidth. The other one will, in the long run, will eventually give you 1/2, but with some delay.
But in the required period. Right?
In
any period. The first server will give you the bandwidth immediately, whereas the other one will give you later in the same time interval.
Yes, yes.
Okay.
So it's less than equal to longest idle time.
Longest idle time, which is 1. Longest idle time is 1. If for this case, okay? I mean, the drawing was here.
Okay. Yeah.
I have to remember to correct this. Okay, now let's make an example. I will do this together with you to see, to schedule, can we schedule 2 tasks over a periodic server? We just see. Okay. Well, let me draw the supply bound function. Supply bound function, if you have a period of 4 and a budget of 2, is 0 until 4. Then it increases until 4, it is 0. Then at 6, it goes to 2. And until 8 is flat. So the period is 15. I need to do it for a while, for quite an interval. 10, so at 10 it's 4. Then at 12 it is at 12 it is 4 flat. At 14 it is 6, and it is flat until 16. And let's say at 18 it is 8. Yes, something like this. That's it. It's flat 4. Then 6. See avanti. That's it. 10, 12, 14, 16. Yeah, should be something like this. Okay? We are wondering about if these 2 tasks can be scheduled over a virtual machine implemented by a periodic server with period 4 and budget 2, which then has this supply bound function. Okay? By fixed priority. Well, fixed priority, if you take a look at the slides, we have to check if for all I from 1 to 2, we have 2 tasks, exists a point we can restrict to this deadline set that I defined in the last, well, maybe the first or in the second class, such that CI plus the interference, I mean, whatever it is now, Well, let's write it down. Okay, then now let's write it again. Is less than equal to SBF of T. Okay, we just check this. So we do I equal to 1. I equal to 1. If you don't remember, T has to be equal to just the derivative, 7. Okay, is it true that C1 plus nothing, because there is no interference for the operating task, less than equal than SBF of 7? Is it true? So we have to check if 2 is less than equal than SBF of 7. SBF of 7 is here. So we have this point here. So we have to check if SBF at 7 is less or equal. It's okay, because SBF is exactly 2. So the first task is guaranteed. So let's see if also the second task is guaranteed. I equal to 1, and the set, the strange set pi, blah blah blah, now is composed by 14, and let's go somewhere where I have more space. I go up here. I equal to 2, t equal to 14. T equal to 14, we have C2, which is 2, plus this C2, plus the interference of tau 1 in the interval long 14, which is 4, because it's 2 jobs times 2 computational time. This is C1. It has to be less or equal than SBF of 14. So basically this is 6. We go at 14. Yes, we can. At 14, the SBF is exactly 6. So we can guarantee also the second task. Okay? We can guarantee also the second task. We don't need to check for 15 because 30 should be 14 or 15, right? We need to check if it exists a point, but we found already 14, so we don't care of 15. Even it could be even wrong, the condition for 15, but then it's true already for 14, we don't care. Now let's check for the linear. Can we guarantee these tasks by using the linear lower bound function? But the linear lower bound function is something that is like this, right? Which is lower. So we can already see that this point is such that the task set is not guaranteed by the linear lower bound function because it's strictly below. Okay? So here is yes. Is it scared with the lower bound function? No. Let's check with EDF a second. Let's see. Well, that no EDF. Wow, that period here is a bit. Well, 15. Let's see. Okay. We have to check at all the absolute deadlines, so we have to check all the pairs. Let's say, well, I write here T at 7. At 7, we have 2 jobs, 2. Then you have at 14, you have 4. And at 15, you have 6. Then you have 21, you have 8. Then you have 30, you have 10, something. Yeah. I mean, to find a point where you can stop to do this check, you can use the usual trick of lower bounding the man-bound function of the task set with a line. Well, at the point where the line will be below, you don't need to check any longer. In this case, you can bound by a line which has a slope. Let's see. Here you have delta equal to the period. So the dBf of t is always less or equal than u1 plus u2 t, which is equal to 2/7 plus 2/15, which is and the fifth. Let me do some math. Let's say. We have to do 2/7 plus 2/50, right? It's something like this. 0.41, okay. So we have to find where this line. So we have a line with a slope which is a bit less than 1/2. In the point where this line intersects the linear lower bound, from that point and on, we don't need to check anymore. Okay, let's compute this intersection. So basically, we have to compute the intersection between delta, intersection between alpha t minus delta equal to sum of u t. The intersection then is at right, alpha minus sum of u t equal to delta, so t equal to delta divided by alpha minus sum of u. And let me do this short math. So how much is delta in this case? How much is the delta of the linear lower bound of the supply function? 4 divided by, how much is alpha? What? Alpha, yeah, the period was, it was, 2 and 4, so it is 1/2, 0.5 minus 2/7 minus 2/50. 49. Wow. Okay, so basically we will need to check all the deadlines until 49. I don't want to do it, okay? You can do it if you want. Because after that point, so after 49, you are guaranteed that the linear upper bound is always above the linear lower bound of the SBF is always above of the linear upper bound of the DBF. So we don't need to check. But until that point, we need to check. So we check, and somebody will check, not me. Allora succede.
C'hai la finestra aperta sopra.
Oh. No. Ah, avevo fatto, vabbè, ragione. Non avevo fatto, no. L'ho stoppato. Okay, so, well, I don't remember if it was scheduled or not, but it is an exercise that you can do. Okay. Now, well, we enter a bit into the design problem. The design problem of how to do this is something that Abby was a bit mentioning. How to design a virtual machine for a given application. So you are given the application. How do we choose the values of your question maybe exactly what are all the feasible supply functions that guarantee the task? Okay. Before doing that, I need this explanation. The design, for example, using the linear lower bound, it's a bit simpler because let me just make an example. Let's say I want to guarantee one task only. To guarantee one task, I just need that by its deadline D, it receives a computation time C. So that's the only constraint I need for one task. What are all the supply functions that guarantees that? Well, are all the supply functions that at D are above, at equal to C or above. So the only constraint is just C less or equal than SBF at D. And that's it for one task. In the linear constraint case, I can do something a bit nicer, because if I'm wondering about what are all the linear lower bound functions that can guarantee, of course, also above, but then I have just to compute all the lines going through that point. Okay, how do I express it? I express it as, so basically I define f of alpha delta, which is a sub-region in the alpha delta domain, function of tw, okay, is the region of all the alpha delta such that what? Such that the linear lower bound function at D is greater or equal than W. Is exactly this. So I define, so this is basically, this point is T and this is W. F of alpha delta TW is the set of all alpha and delta such that their line is above or at this point. Okay? Very simple. Right. So, for example, if the question is, we want to design a server which minimizes some function of alpha and delta, such that the task set which is into the virtual machine is scheduled by EDF. Then what do? We define a problem of this form, which is we minimize whatever cost of alpha and delta, such that alpha and delta of the server is within the intersection of, for all t into the set of deadlines of alpha t the delta of t, which belongs to the set of deadlines, dbf of t. I mean, one of these guarantees one point of the dbf, making the intersection for all t into the deadlines, every pair alpha and delta into this intersection automatically guarantee the schedulability at all the deadlines. So this condition is equivalent to the EDF schedulability. Okay, so it is equivalent to choose an alpha and delta which guarantees EDF schedulability. I mean, if the schedule is fixed priority, since we have exist for all instead of, no, it's for all exist instead of for all t in the deadline, basically we have to make the union of the points into that strange set that I showed you how to compute in the second class. And then once we have made of what? Of t, of f alpha delta, evaluated where? At t and the ci plus the interference. And then we make the intersection for all tasks. So this condition guarantees the schedulability of task I. Then the intersection, you guarantee the schedulability of all tasks in the set. Okay?
Sorry, can you please remind me what J is?
J is whatever cost that we want. So
Like
because No, no, because the schedulability here is implied already by this choice. Because we need to have something. Otherwise, the answer is always to choose the alpha as large as possible. That this is something that translates a sort of price in having a high bandwidth. Otherwise, if you have no price, it's choosing a high bandwidth. Bandwidth is infinity. Yeah, you can always find something. So to have a well-posed problem, you need to have some price in bandwidth. Otherwise, it's always complicated, right? Yes. What is the geometry of some of f alpha delta of some pairs? Is this just in the plane of alpha here and delta? So basically, I mean, this kind of game, if you want, produce this sort of shape of this way, which is convex. And for example, if you do then EDF, since EDF is you have to make the intersection of many of these regions, since each region is convex, then the overall resulting region. Let's say that these are deadline DBF pairs, if you want, then making the intersection, you would get this, which is intersection of convex, and it's also convex. So if you want, you could use the convex optimization to find the optimal alpha and delta when you are with EDF. With fixed priority, since you have also the union, then the region is not necessarily convex.
But it can be.
It can be. It can be in very rare cases. Yeah, but it can be. It can be. It can be. Yes, it can be. Okay. What are, I mean, to come to somehow your question, what are reasonable cost functions, cost in terms of alpha and delta? Well, they have to translate something that we want to achieve. Typically, if we have a given task set, we want to use the minimum amount of bandwidth possible. Right? So typically, good choice could be j equal to just alpha. So we want to reduce alpha as low as possible. So, well, it has a good motivation because we want to have as little as possible. However, it may lead to impractical implementation, because what's the problem? If you want to minimize alpha and we have no cost in delta, basically the optimal will always be delta equal to 0. Why this? Let's say that you have this is alpha with delta with non-zero delta. This with the same alpha and 0 delta. Of course, the line with the same alpha and 0 delta is always strictly larger than this one. So, I mean, there is no convenience if you don't weight this. If you don't say to the optimization, look, I mean, if you let's put it this way, if you let the optimizer choose arbitrarily these two, because these two are equivalent, because if you have a cost alpha, then these two are equivalent because they have the same alpha. Then the optimizer will always choose this one because this one is larger and can increase. So if you have a point here to guarantee, it's always more convenient to do like this if you want to reduce alpha rather than doing this, because this is a lower alpha, right? So I mean, if you don't set any cost into a small delta, then you will always get problems. Well, problems from the implementation point of view.
Implementation as in actual
implementation. No, implementation when you are at the point of translating alpha and delta back into server parameters like Q and P. Because if you have delta equal to 0, then you are going to have a period equal to 0, which is something not really practical.
Which basically means that you have the entire processor.
You have?
The entire processor.
The entire process with a share. You cannot achieve this very fine, with very small share. I mean,
so basically you don't have a share.
Exactly. You have all exactly. So, yes, right. So the point is this: from the expression of delta, if you have delta equal to 0, implies p equal to 0, right? So that means that the period will go be smaller, and that's not possible. So to prevent this delta equal to 0, one good option is to have a sort of weight also on the period. In this way, let's say that the global scheduler mechanism, you have this server that implements a budget and a period, budget and period. Of course, at every period, you have, why this solution is impractical? Why with the solution with period equal to 0 is impractical? Because when you have a periodic server, you have some overhead that is consumed to run the server machine. So if the periods get smaller and smaller, the amount of bandwidth wasted in the overhead goes to infinity. That's why a reasonable way to express that expression is that you want to minimize, of course, we want to minimize the bandwidth, but we want also to minimize the wasted bandwidth, which you can represent as some constant due to content switch overhead, if you want, over the period. Because every period, the server will occur in some operation that you want to reduce also. Okay? Okay. Okay, so now, before I showed you the...
One question.
See.
Is there an optimal, so given a set of applications composed of real-time tasks, is there a method to calculate the server parameters optimally?
Optimal in the sense of?
Optimal in the sense that if there exists a server parameter that guarantees the schedulability, then you can find it. Something like that.
Without any... So without minimizing the bandwidth necessarily, even with an arbitrary big bandwidth, because if you can choose arbitrary big bandwidth, then you know.
Yeah, then it's like the processor. So, but if we minimize bandwidth.
If you minimize bandwidth, yes. If you minimize bandwidth, you can find the minimum bandwidth which guarantees. Actually, the minimum bandwidth which can guarantee an application is the same of what we saw in the last class, well, in some of the last classes, as the minimum feasible speed. The minimum feasible speed is exactly the same as the minimum bandwidth of a virtual machine. Okay? Okay, so something that I wanted to add up, and before we showed the design using the linear lower bound function in that convex expression, right? I mean, if we want to design based on the exact function, the exact SBF, we can do something similar. We can call FPQ as the set of P and Qs such that the supply bound function of those P and Q is less or equal, and evaluated at T, is larger or equal than W. Okay, basically, instead of here we have this point T and W, we are wondering about what are the set of P and Q such that this function is at this point on above. Okay, and then you can use, I mean, all functions like this, and so on and so forth. Now, you can represent this set, I mean, in the plot. For example, here in the figure, I represent all the P and Qs, which guarantees 4 units of time at time 10. Okay, so you set 10 here and 4 here. And you have so this shape like this is an above. Okay, of course, increasing, if something can guarantee the point, by increasing Q, you can always guarantee the same constraint. Right, so what I was saying is that here I draw both the exact region, FPQ of 10.4, which is whose boundary is this one, and here I overlap on the same the region that you would achieve with the linear lower bound function, okay, translated into P and Q. And of course, this is smaller because the linear lower bound has some loss, and you can here the loss is quite easy visualizable because it's this. So basically, the points here are the points for which the server PQ can guarantee this point, but the linear lower bound corresponding to the same server PQ cannot guarantee. Over time, this situation, let's say we have this point 10 and 4, this corresponds to the case where you have, let's say, the linear, well, something like that. Something like that, right? Where you have the exact supply function which can guarantee this point, while the line, the linear lower, cannot because it's below.
Can you quantitatively compare? Can you quantify the loss of bandwidth?
How? It's complicated. Okay. It depends on T and in terms of area.
Yeah.
In terms of area, yeah, you start to do, but then you do the. Yeah, if you want to do the math, you can complete the area. I think the area is finite, but then, you must.
Is it interesting?
It's good that you. Of course, it's good to measure the loss that you introduce with the linear lower bound, but finding a suitable way to measure this loss is not that simple. Because either you end up with sort of random generation of numbers, you randomly throw in numbers. Here, some numbers are in, some numbers are out, so how do you do that? Or you can measure the area. You could measure analytically the area. Here is something that is integrable, and here I think at some point it tends to something that close, so maybe this is integrable too. But I don't know what to do with that. Then, yeah, you find this number, and this is a number of what? PQ pairs. But, yeah. Okay, something that I was also meant to say is as follows. Let's say that you want to minimize. If you want to minimize alpha, alpha is equal to Q over P, right? If you want to minimize alpha, basically minimizing Q over P means that you want to minimize, for the moment, don't take a look at this dotted line. Don't ignore it for the moment. If you want to minimize alpha Q over P, it means that you want to minimize the slope. This is slope. This is Q over P. Right? You want to find the point where this slope is as small as possible. And from this figure also, you see that the points where this slope is as small as possible tends to well, with both P and Q to 0, and a slope, a minimal slope equal to this, right? This is what you get. However, if you introduce some cost. So if the cost, some cost in the period, so let's say that J is equal to alpha plus C over P, so introducing some cost into the period, basically what you get is that, I can show, is that the lines with the same cost are basically slope now going through the point minus C. I can show you quickly, because if you have Q over P plus C over P equal to some value K, some slope, and the same Q over P plus C over P equal to some other K prime. Where do these equations intersect? Well, here you can write P, you can write P. Right, so you have, basically you have Q plus C equal to both QP and Q and K prime P, which implies P equal to 0. If you set P equal to 0, here you get Q equal to minus C. Okay, so the points that where all those lines goes through are the points with P equal to 0 and Q equal to minus C, which is this point. Okay. So now then the question is, you want to minimize, you want to find the line with minimal slope going through this point. What line? What is the point? The optimal point? Well, you try. You find something, maybe this one. And which is nice, because now this point has no zero period. This point has some considerably non-zero period, okay? If instead, if you, it's also nice that if C is what we say is the impact or is the context of the switch overhead. The smaller is C, the smaller is going to be the solution of the optimal period. Because the more you move this point up here, the more the optimal point is going to have a small period. Okay? Okay. Okay, this was right. I think this is the same formulation of the problem before. Basically, then we will want to minimize the bandwidth over the context plus the wasted bandwidth. Instead, if we want to solve the problem on the exact region, in this we have to make the intersections of all these regions, intersection of all these regions. So now it's not convex anymore, it's this kind of strange shape. Main intersection of this region computed again for all deadlets and the DBF at all deadlets. And for fixed priority, you have to do the union of regions and the intersection of region as usual. Okay? And then you have to find the level set, as I said before, are lines going to the point P0 and Q minus C, and you have to find the point where the slope is minimal. Okay, let's conclude. Okay, so today I entered, actually, I took this overview of hierarchical scheduling. It is quite well motivated by the need of composing application which may be designed by third parties and need to be integrated. We discussed a bit also the design problem, and I mean we can design using linear lower bound function in DF, which is somehow easy because it's convex problem, because we are making the intersection of convex regions, so it's somehow easy. Well, with fixed priority is complicated but approachable somehow, because you're also making the union, but still of region which are somehow regular if you want. But then with the exact case, you have that shape, strange shape, which is more involved. Okay, yes, this is the last slide of the course, if you want. So with a very super simple task model, I have gone through through a long journey, if you want. So we have seen fixed priority uniprocessor scheduling, and we have seen schedulability analysis, sensitivity analysis, and a bit of optimal design of the task set. And we have done the same with EDF. And then finally today we also saw the fixed priority NDF over a virtual machine, and we have seen both schedulability analysis and the optimal design of a virtual machine for a given task. Yeah, if you want to publish in this area, you can just complicate the model. I mean, there are many possible. I mean, the area is quite active, so I mean, many things have been published already. But there is space for some contributions. If, for example, you want to complicate the model or the platform model, possibly getting closer to the reality, because this task set is extremely simple. Maybe it's a bit far away from the reality. And yes, and that's it. Okay, so this concludes the course. If there are questions. We stop the cracker now. Otherwise, the people